So hello students, so today we will continue from my last lecture. So recall that in my last lecture, we learn about some property of Bernoulli process, okay, and so what was that? So you have sequence of random variables which are independent Bernoulli with parameters p, probability of arriving something which we are calling success. Okay, uh, given a Bernoulli process, so you have this kind of discrete time interval. Okay, and suppose you have say failure which is not arrival, and then you have a success which is arrival, and then again arrival, and then failure, then arrival, then failure, and then again success means arrival, like that. Okay, so attaching it can be random, so independent, it can be whatever time slot you have is arrival. It does not has any effect on previous or the later one. Okay, so attached with this kind of uh, Bernoulli process, you can attach two more random variables. One is you can call that um, interval times. So what is interval times? Interval time means that that starting from beginning your first success. So this is you will call by T1, and then first interval time. Second interval time means from next to second. So this is T2, and then third interval is like this, T3, and so on. No, third interval is like this. Okay. Yeah, so here is a success, and then from here to here, okay, like that, T4, and so on. So this T1, T2, T3, T4 are the interval times, the length of the intervals for first success, and then after first, T2 is the till next success, and T3 is the after second, and the time interval the third success, like that. Okay, and you can attach one more. So this is we call interval times, inter arrival times. So interval times is nothing but um, we denote by T1 till first success, and then T2 is the after first success, how much time you require till second success, and so on. Okay, so this is called interval times. Now with that interval times, you have one more random variables which is called kth success, kth arrival. So the first arrival is here. So I can write down by y1. So this is first arrival, and then from beginning to second, y2 second arrival, and so on. So I can define one more thing is called random variable is called the kth arrival time. Okay, by this y1, y2, y3, and so on. So you can easily understand that y1 is nothing but t1, and then y2 is nothing but t1 plus t2. Okay, and so on, dot dot dot, and in general for any k, yk equal to t1 plus t2 plus up to tk. Okay, so this first ti is interval times, and this y is our kth interval times. So they are random variables also. Okay, they are discrete random variables. So we can have a natural question: what are the PMF of this discrete random variables. Okay, so let us try to find out, and that is also we have learned from first start property. So once you reach t first success, you t1 finish, and then after first success the Bernoulli process is having this fresh start property. So you will start with again, you want to find out how many trials you require for second success. So this is again a new random variable, right? This fresh start property tells you it is independent. So by our last discussion, we know that T1 is a geometric random variable, geometric random variable. Now using this fresh start property, fresh start property of a Bernoulli process. What do you have? So you know that all those TIs, T2, T3 and so on are also geometric. Okay, so these inter-arrival times are nothing but geometric random variable. Okay, so you can actually define the Bernoulli process by inter-arrival time. So originally we define it by sequence of sequence of random variables. Remember sequence of Bernoulli independent random variables. Yeah. Now you note that this note that is any Ti and Tj and Ti are independent random variable. Okay, whenever I not equal to j. Okay, so now so you can alternatively define. So one can give an alternative definition by this inter-arrival times. Okay, so how they can define this? This is a sequence of so this is a sequence of independent geometric random variable variables T1, T2 and dot with say common parameter P and these stand for these TIs. These stand for the inter-arrival time. Okay. This and proper number 2. So we record a success. So when you say there is a success or arrival happened, record an arrival at time. So T1 there will be first arrival, and then T1 plus T2 there will be second arrival, and then T1 plus T2 plus T3 third arrival, and so on. Okay, this is arrival. So by this also um, one can define the geometric random variable, okay, by interval times. And now what about that kth arrival time? So now let us try to understand that how this kth. So now try to find out what is this, the PMF of yk, kth arrival time, how it look like. So now try to understand that. So if you have kth arrival, so it is nothing but sum of t1, t2 and tk. Okay, and do you know that all those ti's are, so ti's are independent uh, independent. So we can easily find out what is the expected values of yk, right? So expected values of yk by our formula, it will be sum over t1 plus expected values of t2 plus expected values of tk, right? And because ti's are all geometric, so this will be 1 by p plus 1 by p plus 1 by p. So the answer will be k by p. Okay. Similarly, the variance also you can easily find out the variance because they are independent. The covariance of ti and t. Okay. So the covariance of ti tj will be 0 for I not equal to 0, I not equal to j. So you can find out what is the variance of yk. Is nothing but sum of these, and that is sum of variance of ti I equal to 1 to k, and this is nothing but k times 1 minus p to the power p square. Okay. Right. So now do you understand what is this? What type of random variable is this? Okay, so let us find out the PMF, then we will understand. And then so this is, we are giving a new proof of our old random variable which we already learned. So now to find out the PMF, what I need to find out? So what is the PMF? So the PMF of yk at t times, what does that mean? That means what is the probability that there will be k many arrivals or k many success at t time, right? So so this we need to find out, right? So this is what this is, the probability okay, so this is probability of the event and the yk equal to t, right? So exactly the kth success will come at time t, in that discrete time t, right? So now, so this is same as saying that, so this event, suppose this is my event E, so you can write down your E is actually is nothing but intersection of E1, E2, okay, where E1 is what? So E1 is the Tth trial, the last one, the Tth one trial, not last one, the Tth one trial is an arrival or a success, whatever you write down. So that is an arrival, okay. and E2 is what? Before that, so before that you have only t minus 1 many trials, and out of that t minus 1 many trial you have exactly k minus 1 many success, right? Then total number of success will be k. So exactly k minus 1 any success or arrival. Okay, so yeah, so or arrival, whatever you write down. So these occur in the first t minus 1 time trials. Okay, so if both E1 and E2 happened, then E happened. So this is the intersection of E1 and E2. And now if you know the probability distribution for E1 and E2, then we know the probability for this event E, okay, and that will be nothing but the PMF, right? So this PMF we want to find out, and we see that that depends on these two events. Now try to find out this probability for both. Now what is the probability probability of E2 E1, say that the Tth one is a success, right? Now Tth one is a success. um, okay, so okay, so and also one more thing, so this Tth one is success with probability p, right? So this will be nothing but p, and probability of event E2 is what, that out of first t minus 1 k minus 1 will be success. So now how many ways you can choose your arrival or success? It is nothing but t minus 1 choose k minus 1, right? Out of t minus 1 you have k minus 1 many success, and then probability of success is for each case p, they are independent, so it will be k minus 1, and rest are failure. So what are the rest? Rest are nothing but 1 minus p, and then so t minus 1 minus k minus 1, so this will be t minus k, so t minus k, right? And hence the PMF will be look like PMF of yk at t will look like product of these two things, product of p e1 probability of e2, and which is nothing but t minus 1 choose k minus 1 p power k and 1 minus p power t minus k, right? Now hope we can understand, we can recognize this PMF. This we already learned before midterm. This is called negative binomial distribution. So negative binomial random variable. This also have a name. This is also called Pascal PMF. Pascal PMF. Okay. So what we learn? So we learn that the interval time is given to a variable, and the kth success or kth arrival follow the negative binomial or the Pascal random variable, right? Now let us give you an example. So an example. Now suppose maybe okay, so we can give an example. So suppose in a football match, okay, So in a football match, it, okay, so in each minute of a football match, so a player commits a single foul with probability P, and no foul with probability 1 minus P. Okay, so and the number of foul in different minutes are independent, assuming that different minutes are assumed to be independent, independent. Okay. So and a player say will a player will say foul out of the game once commit so suppose something is 10 fouls, something like that, I mean whatever. Okay, 10 fouls. Okay, and now so now in a suppose, so the question is that what is the EMF of playing time of a player in a 90 minutes game. Okay. So how to solve this kind of problem? So you try to understand and that it is kind of a Bernoulli process with parameter P. So this is kind of a Bernoulli process with parameter P. Okay, and so total number of So playing time is what? So you define the playing time, say x, random variable. So what is x? X is um, either you have uh, arrival. Here arrival is what? Arrival means a foul, right? So you have kind of you divide into the time slot into each minute, and there are 90 slots. Okay, so you have no foul, no foul, and then you have foul. Foul is here success. There is no foul here, and then something again foul success, right? Clear? So the moment he reach 6 success or 6 foul, he will be out of the game, right? So and this is nothing but what? So this is first one is y1 and then y2 and y6, right? So it will be either y6 or 90 minutes, whichever is the minimum. So that will be the playing time, right? This is the playing time of the player, right? Now what is y6? So y6 we know that this is a, we just learned that this is negative binomial random variable, right? So we already, so this is also known that PMF of y6, okay, at any time t is nothing but t minus 1 by 6 minus 1, which is 5, into p power uh, p power 6 into 1 minus p power t minus 6, and your t will start from 6 7, right? So you need at least 6 minutes time to get a 6 foul. Okay, so now 1 minute. So what was my question? My question was 10 fouls, sorry. Yeah, so 10 fouls. So this is y10, so not y6, y10, okay, till y10. So here also we have 10. So y10, so this is 9, this is 10 into t minus 10, and this is minimum 10, 11, and so on, right? So now this is already known, right? Now we need to find out what? We need to find out what is the PMF of playing time. So PMF of playing time is what? So this is probability that x, and x is something, say x, and this is what? This is probability that x will be equal to x, which is nothing but okay. So there are two cases. So we first consider the case when my x is in between. So x is in between. Okay, so 10 to 10 to x cannot be less than 10, right? So x is in between 10 to 89. Okay, so till there are 90 minutes time, so it can be x to 89, and in this case so in this case what happens? In this case probability x equal to this, and that will be what? So that means that when x equal to 89, then player go out of the game. So that means the last foul, the 10th foul come at the time this, right? So that means this is probability that as y10 happened in that x time x, right? Whenever x is in between this, right? Clear? Okay, so this is equal. So if the person had a foul at x minute time, which is in between 10 to this, then he will go out, right? And that will be following this above law. of negative binomial distribution, and then you'll have, it is nothing but x minus 1, 9, and p to the power say 10, 1 minus p to the power x minus 9, x minus 10, and here x can be in between 10 to 89. Okay, but if there is he did not happen, so this is for this, and the case, and the case number 2. Yeah, so the case x, so there is no foul there, there is no 10th found in 90 minutes time, right? Then what happened? Then it will be nothing but, so so you find out the sum of all fouls and then take so what will be this probability of x equal to 90, sorry, at 90, so what will be this? This will be 1 minus all the fouls before 90, right? So then probability of x, and your x will be from 10 to 89, right? So you have this probability distribution, the total probability distribution will be 1, so you sum of all those things and then take minus, so this will be the probability law for the person if there is no 10 foul in 60 minutes 90 minutes game, right? So this is one of the example where you can use Bernoulli process to calculate this type of problem, right? Now if you know what is P, the probability of foul, then you can easily find out what are the probabilities, right? Okay, so now there are some more things you can do. So you can now we will learn something called splitting of a process, splitting of a Bernoulli process. Okay, so what do you mean by splitting by Bernoulli process? So suppose you have a Bernoulli process is running. Okay, so one Bernoulli process is running, and I have these arrivals which I am writing, say suppose failure, arrival, failure, say arrival, then failure, arrival, something like that. Okay, and failure, arrival, right? And this is with probability p. The p is what? P is the probability of arrival at any discrete time. Okay, and the complementary probability is 1 minus p of not an arrival. Okay, so suppose for example this is kind of arrival of Gmail, arrival of email into my inbox from say IIT Ropar domain. Okay, now I have so decided to keep that email or not accordingly. So if I find out that, so these two are not arrival from, so failure means here they are not from IIT Ropar email ID. Okay, and now the third one is a arrival from IIT Ropar email ID, but I may keep it, I may not accordingly. So this is my file, say MA203 file. Okay, so if I see that this arrival, this mail is from one of my student of 203, so I will keep it. if it is not a mail from my student, then I will not, I maybe there will be another file, say, so let me write down, so another file like this. Okay, and if it is mail of so this is if okay, and third one is a student, so you arrive here, so it is not here in this file folder, sorry, this is if. Now the fourth one, if it is a arrive, suppose this mail is not from student of the course MA203, so I will not keep it here, so this is not an arrival. Okay, so then I keep it here, so this is arrival. Clear? And then the next one is also is not an arrival, so it's not an arrival here also. And again this one, so this arrival, again you have two choices, either you put here or we put here. So if I put here arrival, then this is a failure here. Okay, now if you put it here an arrival, then it will be failure here. I mean, clear? So like this. So what happens, so the original process I have background into two processes. Now keeping this arrival to my this folder, having a probability, suppose this probability of keeping this is say q, and so hence probability of not keeping this thing here is 1 minus q, and this probability of keeping a file is independent to any time slot. So I can, if I can keep here, does not mean that I cannot keep the next one, I can keep next one also, right? So this is independent. So what does that mean? That means given a Bernoulli process, you can split the Bernoulli process into two. Even inside that also you can split many more places. For example, here also, the last one also I can split accordingly, that this mail is from my PhD student or not, or from my math department colleague or not, like that. Okay, so you can split the process into more number of process. Okay, and then still after splitting also it will be again a Bernoulli process. So this will be again a Bernoulli process, and this will be also again a Bernoulli process. Okay, so now the question is that if our original process was Bernoulli process with probability p, then uh, so the uh, process the process arriving process so how to write down, so process of arrivals, so you can write down arrival arrivals, you can write down this keep and discard, right? So in discarded, so this keeping process, so this is with probability q and this is with probability 1 minus q, and originally the process was probability p. So what does that mean? So if you keep one thing with process, what is the probability of keeping this process? Is nothing but p into q, right? So in this uh, a time slot having arrival or success with probability uh, pq, right? And here a time slot having arrival with probability, so this is arrival, so this probability will be originally it was p and now it is 1 minus q, so p into 1 minus q, right? So both will be Bernoulli process with probability, the first one will be probability pq of an arrival, and second one will be probability p into 1 minus q for an arrival, right? Clear? So and then similarly you can have something called merging of a Bernoulli process. So write down that merging of a Bernoulli process. Okay, so what is this? So we just learned that we can split Bernoulli process into more than one Bernoulli process. Now we can do the opposite also. So if there are two Bernoulli process, for example, so I have a Bernoulli process here. Okay, so one, two, so something, and then I have say arrival, failure, arrival, and then failure, like somewhere arrival. Okay, and then I have another Bernoulli process, and this is uh, probability P with probability P and another Bernoulli process. So arrival, arrival, failure, like this. Okay, with parameter q, then we can merge these two process or something called adding, and then you can get a new process. What is then my new process? So I will check in my first time slot if it will be arrival if at least one of these two arrivals. Now you see that this one this one is an arrival, so I will put arrival here. Okay, here both arrival, so again it is arrival. Okay, so the failure or not arrival will come only if both are failure. Now in the third space you see that both are failure, so here I will put failure. Okay, clear, and so on. So merging means what? So the new process, inside the new merging process, you will have an arrival if at least one of that place will be arrival from the old two process. Okay, and so now you see that this is also again a Bernoulli process. Bernoulli process. Now question is that what will be the probability of arrival here, right? And that is we can easily compute. So you see that probability of failure is what, or not arrival is what, if both are failure, right? Now in the first case the probability of failure was or not arrival was 1 minus p. In the second case it was 1 minus q. Okay, and this thing here failure happened if simultaneously the failure happened in the first process and second process, right? So so probability of uh, of not an arrival in the merged Bernoulli process will be what, will be 1 minus p times 1 minus q, right? And hence probability of an arrival in the new merge process will be what, will be 1 minus this probability 1 minus p into 1 minus q, right? The complemented. And what is this? This is nothing but p, and then you have q, and then minus and plus minus, so this is minus pq. Okay, so this will be the new probability arrival into the merge process. Clear? So given a process, we can split into two and more than two, and also we can merge in. Given more than two processes, we can merge into a single process also, right? Clear? Okay. So this is some of the properties of Bernoulli process, and now we can also have you can also approximate this process. Whatever we learned already, it is called Poisson approximation, you remember. So just try to let me recall it. Poisson approximation to the binomial. Okay, binomial random variable that we only run, right? So what does that mean? That means suppose we have uh, suppose we our arrivals are coming, see, number of arrivals or number of trials is huge, number of trials is huge, and that arrival length of the time, arrival times, so our time slots are very small. Okay, so that the expected value, so n is large and probability of, so the interval is small means probability p is small, and but np is something moderate. Okay, something mt is something okay, it's a moderate thing. Okay, so then what we learn in our earlier classes, then we can approximate this process into Poisson approximation, and then the number of success, suppose number of success arrival is the number of arrival, then we can find out the mass function. So mass function will be something, the limiting case, right? So limiting case will be what? So you can write down that n choose k and sorry at k, n choose k p power k 1 minus p power n minus k was original, and then here what is happening, so here you know that um, so this is moderate lambda np. Okay, so we will change it to lambda. How do we change it to lambda? So we write down this p, instead of p we write down lambda by n, and then we check n tends to infinity, right? So if we follow this process, then we know that this process is converts to uh, this Poisson random variable, and what was that? That is e power minus lambda and lambda power k by factorial k, and it is true here also. So whenever you have n is very large number of trials and p is very small, such that np, which is lambda, is moderate, then we can approximate this process by Poisson random variable. Okay, and this is an important observation, and this gives us two idea to extend Bernoulli's process to a continuous version, which we will learn into our next lectures. Okay, and that is called a Poisson process. Okay, so we will learn this thing in next lectures, which is called Poisson process. So I will stop here.